Hi, everyone. So today we have Nancy Wallace from UQAM, who will be talking about the unexpected relations between parking function formulas, pattern avoiding permutations, and the Robinson-Schensted algorithm. If there's questions, she can't view the chat, so either you can put it in the chat and I will read it, or just unmute yourself and go ahead and ask. Questions are always more than welcome, and Nancy has said she will answer every question, no matter what it is. So have fun with it. All right, take it away, Nancy. Thank you.
Okay, well, thank you for inviting me. Today I'm gonna start by a little bit of history, and then sadly a lot of definitions. And then for part one, I'll talk about parking function formulas. And then in part two, I'll talk about pattern avoiding permutations and the Robinson-Schensted algorithm. So the Nabla operator of François Bergeron, not the same Bergeron, and Garcia as the modified Macdonald polynomials as eigenvectors. And Ayman proved that the Frobenius characteristic of this the diagonal harmonic modules were Nabla to the En. So from Bergeron's work, we can see diagonal harmonic modules as GL2 SN modules. If you want to know briefly how it works, for two sets of variables, the action of GL2 SN is a GL2 matrix that acts on the left of the matrices of variables, and a SN matrix that acts on the right of the matrix variables. So there's related work that includes Zabrowski's super coinvariant modules and Rode-Wilson's Vandermonde in superspace. And there's also many applications to the coefficients of the bicharacters of these modules related to knot theory, physics, and algebraic geometry. So I'm gonna start with the first definition. I'll give the motivation later. So a shuffle of two words is the set of all the words that have U as a subword and V as a subword. So you can just see it as we have a word here and we have a word there, and we're just looking at all the ways we can mix them together. For example, 3-4 shuffle to 1 is the set of all of these permutations. And 3-1-4-2 is not in the set, since 1-2 is not in or is out of order because it was supposed to be 2-1. So for pi and sigma permutations, sigma avoids the pattern of pi if there's no order preservation morphism from pi to sigma. For example, in A4, 4 it's like a subset of S4, the symmetric group of 4 elements, well, not 4 elements, but 4 numbers. That avoid 1-3-2 and 3-2-1 are all these permutations. So clearly 4-1-3-2 does not avoid 1-3-2, but it also does not avoid 3-1-2, since the 4-1-2 in the, can you see my cursor when I displace it like this? Yes?
Yes.
Okay, so the 4-1-2 are order isomorphic to 3-1-2, so it does not avoid 3-1-2. And general AN 1-3-2 3-1-2 is the shuffle of the k+1 to n and k to 1 in decreasing order. So I don't know if you know partitions and tableaus. I'm just gonna go quickly over them in case you don't. Partition is a decreasing set of integers, and you can see them as a tableau and as a diagram in this fashion. you put all the boxes like this in decreasing order, and you get a kind of stair-shaped diagram. And we can write them in Frobenius notation by putting this part in the first number and this part in the second number. So in this case, it's 4, 1. It's a partition of 6. So for partition, the standard York tableau is a filling that uses all the numbers from 1 to n, and there has to be strictly increasing in the columns and rows. Like, for example, here we have numbers 1 through 5. We have 5 boxes, so this is okay. And increasing in all the rows and columns. This is a tableau that works. So the descent set and the major index for the tableaus is the entries i's, such that I plus 1 line the row strictly above. So big D is for the set and small d is for the number of descents in the set. The major index is just the sum of the i's. So in this example, the ones in reds are the descents because 3 is over 2, so 2 is a descent. 5 is over 4, 4 is a descent, and so on. And the descent set is here. Here is the number of descents. We have 4, and the major index is 19. So now we go to paths. A dig path is a path that's as northeast steps and stays above the main diagonal. So here we have a northeast, 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 east, east, northeast, northeast. And if we decide we would like to add a permutation on the side of this path, stuck on the path, where it's increasing in when the north steps are consecutive, like this, 4, 5, 8, 1. This is a parking function. And the reading word of the parking function is the word that you read from the diagonal furthest from the main diagonal to the middle and from top to bottom. So here we would have 6, 7, 5, 4, 3, 8, 2, 9, 1. And if it's not the reading word, usually it's from bottom to top. So it would be 1, 8, 3, 4, 5, 7, 6, 9, 2, if we don't say it's the reading word. So in this particular case, our reading word is a shuffle of 6, 7, 9, 5, 4, 3, 2, 1. And when these are shuffles, such shuffles, or avoiding 1, 2, 3, 1, 3, 2, 3, 1, 2 permutations, we can change them into Schroeder paths, because you just have to consider all the steps associated to the increasing numbers as diagonals, and you have the Schroeder path. So this would be a Schroeder path of 4 diagonals, because we have 4 diagonals and we also had 4 here. So I want to consider special Schroeder paths that have a north step at the top line. It doesn't have to be here, it could be here, 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 but the last line has to be a north step, not a diagonal step. And we'll name this set tilde Schroeder path ND, N for the number of boxes of the grid and D for the number of diagonals. So the area is the same for both. The area is the number of boxes between the path and the main diagonal. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And well, we want the definitions to fit, so it's the same thing for the other one. Are there any questions so far? If I'm going too fast, you have to say, okay. So there's a DINF statistic on parking functions that works in the following way. When you have in the same diagonal from bottom to top, it's increasing, it counts as 1. So here 1, 9 counts as 1, 1, 2 counts as 1, but 9, 2 doesn't count. 8, 3 doesn't count, 8, 4 doesn't count, but 3, 4 counts. 5, 7 counts, 5, 6 counts, but 7, 6 doesn't count. And you also add the ones that are 1 immediately above and compared to the ones that are under, but in the position higher. So here there's no line above, so we don't consider anything. Here 8, there's 9 and 2, but it has to be decreasing. So 8 and 9 aren't decreasing, they don't count. And 8 and 2 are decreasing, so they count as 1 more. 3 and 2 count as 1 more, 4 and 2. And then there's no numbers on the diagonal right below this one here, so there's none that count. So total, we counted 8 diagonal inversions. You could do the same here because we just explained that it's actually associated to a word, but there's another statistic that you can use, which is bounce. And to consider bounce on the Schroeder path, you have to first disregard the diagonal steps and do a bounce as in the dig path. So like throw a ball up, but you don't count this path because we disregarded it. So it goes up here and then it bounces because it touches in each E-step. Each time it touches an E-step or the main diagonal, you change direction. So here it bounces there, it goes up, oh, here diagonal, so you disregard, you go to the next E-steps, it bounces, and then it's pretty much finished. So then you count without considering the diagonals, the places where it bounced. So this is 0, this is 1. We are still at 1 because diagonals don't count, so we have 1. And then this still doesn't count. This is 2, this is 3, so we have 1 and 3. 1 plus 3 is 4, so this is for that 4. And then we add to this another statistic, which is the number of diagonals that are over a peak. So here we have 1 diagonal over this peak, and here we have 3 diagonals over this peak. Again, 1 plus 3 is 4, so here the bounce is going to be 8. I don't know. There's a Zeta map that switches area to div and bounce to area. And bounce doesn't work for parking functions in general, but they do work for Schroeder paths. And well, they just make easier proofs. That's why I'm using bounce. And in this case, div and bounce are the same, but usually they're not, but in some special cases they are. Like when area is 0, bounce and div are the same. So now we can start with the parking function formulas. So here the shuffle theorem says that nabla to the en is the sum over all parking functions, q to the area, t to the div, and this is the fundamental quasi-symmetric function. You take the composition of the inverse of the descent set of the inverse of sigma. And Aglon showed that if you want the coefficient of the Hooke-Schur function with d plus 1 parts on the bottom and n minus d minus 1 on the column of the partition, it will be q to the area, t to the bounce of this of the set of all Schroeder paths that end with north on the top line. There can be e steps after, but it has to be north. There can't be diagonal and east at the end. It has to be north and east at the end. Okay, so given these two formulas that I just described and the Stanley-Lustig formula, which is for q equals 0, that says t to the mag, for all, it's a sum over all tableaus in Sn, t to the mag, Schur function indexed by the partition with shape lambda. Well, lambda t is the shape of the tableau. Okay, the dream would be to decompose all the GL2SN modules of diagonal harmonics into irreducible bicharacters. So what I would like is sum over two Schur functions, one in Qt and one in X. Here, all the functions are either fundamental symmetric, quasi-symmetric functions or Schur functions in X, but there's no Schur functions in Qt. So just quickly, for Schur functions in Qt, there's no, in the decomposition, there's never a partition that has length bigger than 2, because the number of variables has to be higher than the number of the height of the partition. And if you have a 2-part partition for a Schur function, this is the polynomial you get. And if you have a 1-part, this is the polynomial you get. And when you put QRT equals 0, you get just this, this part. So looking at paths with area value 0 is the same as considering Q equals 0. And it's also the leading polynomial in the Schur function. So you can just look at, if you want, if you know the leading polynomial, you'll have the decomposition. And looking at paths with area value 1 is the same as looking at Schur functions indexed by a hook for Qt variables. So what I have is just a formula for certain special cases. That's over a sum of tableaus. This one I'll talk about later, and this one I'll talk about now. So here, actually, when it's 1-part, I can show that it's the sum over all Schroeder paths of area 0 and Schur function to the bounds. And for this one, I don't only know the leading coefficient, I know all the paths that come into play for that Schur function. For example, I have this algorithm. You start with the area 0 function, and then you slowly sort them, bringing the E steps to the right. And this only adds 1 to the area and takes bounds down by 1 for each step. So you get all the paths for your Schur function. So this would be bounds 4, area 1, bounds 3, and so on. So this, like I said before, is the Schur function S4 Qt. And if we look again at this formula, what I'm saying is that you look at the bounds of this one, it will be your Schur function, and you use this algorithm if you want to know all the paths that come into play in that Schur function. It also gives a bijection that switches area and bounds between paths. So
may I ask a question?
Yes.
So in your previous slide, how do you determine the shape of the starting path?
Any Schroeder path that starts with area 0, you can do this to it and it's gonna work. You do the algorithm to any Schroeder path of area 0 and it's gonna work. And it's they're all different. If you start with one given area 0 Schroeder path, you'll never end up with at the third step with one that you add in another using a different Schroeder path of area 0. They're all distinct.
Okay, thank you.
And if you want to know how it works, it's really you just starting from the rightest E step, you slowly bring it to the right one time each time. So here we switched it 1, And then this one was the right is east step. We switched it one, and so on. And this is how the sorting algorithm works.
And so the starting number of paths is what, 2 to the n or 2 to the n minus 1?
Yeah.
Okay. And then at any level D, I mean, D ends up being like how many steps you take, or how many?
Well, yeah, actually, I'll talk about this later. There's a bijection between, well, you can see Schroeder pass of area 0 as northeast pass in the staircase shaped grid.
I have some doubt about that 2 to the n minus 1, because
it's because I'm restricting to Schroeder paths that the last step is not the last, but the last step that's not an east step is a north step. It can't end diagonal east, east, east. It has to end north, east, east, east.
Yes, but can't you just put some diagonal? Oh, I see. Oh, yeah, okay. I see. It's just the number of subsets. I see it. Okay. Thank you.
It's because the reason why I'm restricting to the ones that end with north is because Haglund's theorem, if you want it to be a sure function, you have to restrict to a north step at the end, or else it's going to be elementary times homogeneous. So if we compare the last formula to the Stanley-Lustig formula, like I said before, putting q equals 0 says this is t to the bounce. So there should be a bijection between a Schroeder pass of area 0 and tableaus such that bounce of the path gives maj of the tableau. And this is what I did. So for each tableau of hook-shaped tableau, you can associate a path by, well, the last one has to be northeast because of the restriction. And then the other subset of path is going to be northeast if I-1 is in the descent set and diagonal otherwise. Like here, the descent set is 2 and 3. So here we have to put northeast, but 1 is not in the descent set. So this is diagonal. 2 is in the descent set. So it's northeast. 3 is in the descent set. So it's northeast, diagonal, diagonal. And I can do because the previous theorem that I said I'd talk about later is for hook shapes. So there's also a bijection for area 1 path, which starts by a cyclic action. So we start by just associating families of Schroeder paths of area 1, where you only change the place where you put area 1. The main structure is the same, but here you put area 1 there, and this one, next step, you put it in the next northeast, and then you put it in the next northeast. And you do the same for the diagonals, but you only switch diagonals. So north, when the area is north, north, east, east, area 1 is north, north, east, east. They stay in the same family, and it's going to be always north, north, east, east. And when it's diagonal, it's always going to stay north, diagonal, east. And I say cyclic because I consider that when you come here, you can go down there. But if you don't consider this one and you consider all the other ones, the bounce goes up by exactly 1. So this is how you get this minus y for the other one, minus I for the other one. Because 2 to the n minus major index of a conjugate of a tableau is actually the maj of that tableau. So Here it's like R-1 to choose n plus match tableau would be the same thing. And the minus I is related to which one we're picking here. And for these, I also found a bijection into tableaus that's a little bit more complicated, but basically the same. It seems more complicated because we have to say where's the northeast east and north diagonal east, but it's also related to the descent set. So for example, here, one is where we decided to put our, starting from the bottom, one is where we decided to put our our area 1 box, if you might want to see it that way. And then since 1 is there, we know it's a northeast here. It won't be a diagonal. And then 3 is the other place where there's major index. So here we're counting how many, like this one could be 1 or 2. There's only 2 spots where we could put it, since it has to be between a north and an east step. And 3 is where it's going to be northeast, because 3 is in the descent set. Here, 1 is not in this descent set, so it's going to be a diagonal. And since we chose 2, it's going to be in the second, on the second northeast step, so it's going to be here. And since there's 2 and 3 in the descent set, this is northeast and this is northeast.
Hey, Nancy.
Yeah.
So I forgot to mention this at the very beginning. So normally we do like a break in the middle of the talk. So just a warning, it's been about 25 minutes. So it's probably a goodish time to find a place to put a break, if that's okay.
Okay.
But yeah.
Actually, could you wait 2 slides?
Yeah, that's okay.
Okay. So if we take the composition of the 2 maps, like for a tableau, we do the first map that goes into a shorter path of area 0, and then the algorithm, which goes just 1 step to an area 1, we get this path. But if we take this tableau and then do directly the bijection for area 1 and push the area 1 the furthest to the top, we get the same path. So actually the 2 bijections commute in a way. So if we want to look at this as say these are all the partitions you could have indexed as a Schur function in the x variables, and this would be the Schur functions in qt variables. What I found are the dots in black. Like here I have all the area 0 for all parking functions that I know how to do, and all the area 0 paths, and the top ones for specifically hook shape of hook shape here and hook shape there. So if you want to see this as a Tamari lattice, because if you restrain to only dig paths, you can see this as finding the biggest chain of paths in the Tamari lattice that works with the Qt variables. And then we'll go to part 2 after. Okay, so here, like promised earlier, we're going to go with paths again, but this time we're going to define a staircase grid, and the start point is at the bottom, and you can finish wherever on the diagonal of the staircase ends. And for this, we can make a bijection between Schroeder paths with area 0 by simply, when it's a northeast section, we transfer it to north, and when it's a diagonal, we transfer it to east. So this would give this path, but we end up having an extra, because Tn is in an n-2 staircase grid, and here it was for Schroeder paths of height n. We have an extra north path, but since it's always going to be an extra north path, we can just throw it away. And now the area of this is all the boxes that are southeast. So in this case, we have 23, and they're actually the same as the bounds. So the ith is going to be where the endpoint is. In this case, ith is 4. And it also happens to be the number of diagonals. So actually, this object comes from a multivariate formula that I did 2 years back. And I was doing something different on it. Now I'm going to do something different on it, but that's where it comes from. So we have a map from 213, 231 avoiding permutations from actually no, for that we're going to denote like this, from a path to a 213, 231 avoiding permutation. That's actually going to be a bijection. So what we do is we label from 1 to k, the k being the number of e-steps, the paths that start like this, that start with a node, and we label the nodes, not the path. So the node that start with a node and followed by an e-step. So here we have 1, 2, and 3. 8 is not 1 because it goes down. And we label from k plus 1 to n-1 this way. So it basically, you just follow the path and label this way and then label that way. And the word you're going to get is the word, the word you need to have this bijection is the word you read following the path. And you can easily get the inverse from the same path by labeling 1, 2, 3, 4, 5, 6, 7, 8, because, well, that's the way you usually get the inverse. So this is a bijection, and it preserves the match and area. So the major index for the permutation we obtain by doing this is the same as the area. The descent set is the same as the ith, which is also the same as the descent set of the inverse. For the inverse, the major index is a little bit different. Actually, it only depends on the ith. And as a corollary, if we sum all the permutations major with the q to the major index, t to the descent of the permutation that avoid 213, 231, it's actually this generating function. And we get this when we use the inverse of each of the two. So the Robinson-Schensted algorithm, I'll show by example what it is. You take a permutation, then you take the first number, you put it there, and you label 1 in the Q tableau for saying this is the first box that I put the number in. Then the second insertion, you take the second number, which is a 3, and you look, oh, it's not smaller than, it's not bigger than the 5, so I'll just go push the 5 and take its spot and put 5 on the second row. So go to put 5 in the second row. Oh, there's no number there, so we can just put the 5. So the P tableau becomes 3, 5, and the Q tableau becomes 1, 2, because we added this box. Then for the third insertion, we take the third number, which is 4. We go here. Oh, 4 is bigger than 3, so we just stop there. We put it there, and we add a 3 to our Q tableau. Then take the fourth entry. You enter it in the first row. You see, oh, it's not bigger than 4, so I'll just push the biggest number that I'm, the lowest number that I'm bigger than. You push the 3 because there's no number smaller than 1. Then you take the 3 and put it in the second row. The 3 bumps the 5. So you put the 5 in the third row. Oops. So you get these two tableaus. Then for the fifth insertion, you put the 2 in the first row. It's not bigger than the 4, but it's bigger than the 1. So you bump the 4, put the 4 in the second row. It is bigger than the 3, so you stop there, and there you have your PQ tableaus for the RS algorithm. So the proposition is that you can actually read the Q tableau directly from the path when it's a 2-3-1-2-1-3 avoiding permutation. You actually just take the nodes that are followed by a north step. So your 8, 7, 6, and 4 are the numbers in your column, and that's going to be your Q tableau. So I have same types of result for other pattern avoiding sets. I just didn't say them all. And if you take, consider a map gamma that goes from 2-1-3, 2-3-1 avoiding permutations to 1-3-2, 3-1-2, that actually takes a permutation, sends it to a path, and then gives you another permutation. You just compose the two previous maps. Well, then it preserves the Q tableau, and it gives you the evacuation tableau of P. And actually, when gamma is a Schroeder path, the Q tableau of the 2-1-3, 2-3-1 avoiding permutation that you can get like by the bisection phi I said earlier is the same that the map that I gave at the beginning that gave it a tableau for each Schroeder path. So actually the path, I'll go back, the path, the map here, if you take the other way around from tableau to, from path to tableau, is actually the same map than taking the Q tableau of the 2-1-3, 2-3-1 avoiding permutation associated to the path. And I have other results of this type. So this gives formulas for the sum of pattern avoiding permutations where you see them as parking functions with area 0, the Q to the area, T to the div of the path and the word is equal to just taking a path in the staircase grid, taking the area and the fundamental limits, the fundamental quasi-symmetric function, where the composition is only the E steps of your, the composition of the E steps of your path. And I've further work is to expand all the work done for Schroeder paths to avoiding permutation families that I mentioned. That way, if I have the algorithm, I could go get all the functions that go for each sure functions or quasi-sure functions. And if I all expanded or labeled parking functions, if we get the formula, we could see if it works with conjectures involving modules, like Zobraki's conjectured modules or the multivariate diagonal harmonics. Thank you for listening.
Awesome. Thank you for the talk. You ended a little early, so I wasn't ready.
Sorry.
No, it's okay. Give me just 2 seconds and we'll get this ready. Awesome. Thank you very much. Are there any questions? Nancy?
This is such a turn down. The sound effect too long, you know, like boo,
Listen.
boo to sound effect, yay to talk.
I failed. It's my fault. Are there any questions? Nancy, I had to mute you, by the way, so you're muted as a heads up.
She's still muted.
So what are the avoiding permutation conditions say about the insertion tableau, the shape of the tableau? Does it
Actually,
tell you that
it's always going to be hook shaped, and actually I also know that I didn't give all the results because I thought I didn't have enough time, but I think I was scared of missing time, so I went faster at the end. But I also know how to get the P tableau, the evacuation tableaus, and all of the related tableaus.
So does that characterize them? Can you just say, let's say I wanted to generate all these words, would it just be all pairs of hook-shaped tableaus and then convert them into words? And that's the thing you're summing over?
Actually, for 132, for 132, 312 avoiding permutations, and for 231, 213 avoiding permutations, like those two sets, the Q tableau is enough to know everything because the P tableau is fixed. But for other sets of permutation, the P tableau change. So it's enough to sum over the Q tableaus. And like I said, I want to try to expand the algorithm that goes to other area using this, because using the same type of word makes it easier to have nice reaction to them, because I won't be able to use bounds. That's why I'm restraining to pattern avoiding permutations to make the expansion easier. Because for now I can expand it to, well, I haven't had time to write it up because I'm writing my thesis, but I do know all the functions that, all the paths that go into a shape in Qt. Like I can extend my algorithm starting with area 0 to an algorithm starting with area 1. And they'll still all distinct and everything you need.
Are there any other questions? All right, seeing none, let's thank the speaker again.